The main power supply provides up to 90,000 volts to the injector end of the implanter, where the ion source assembly is housed. Inside is a small arc chamber. When powered, a tungsten filament heats a cathode, releasing electrons which accelerate toward the positive walls of the arc chamber. A magnet surrounding the source assembly creates a magnetic field that forces the electrons into spiraling paths. This increases the number of collisions that will occur between the electrons and gas molecules. As a result, more ions are created. Phosphine gas has one phosphorus atom bound to 3 hydrogen atoms. It flows into the arc chamber and collides with the spiraling electrons. This creates a variety of positively charged ions and molecular fragments. Millions of these ions and fragments flee the positive arc chamber through a small aperture as they are drawn to the negative potential of the extraction assembly. They move as a single beam, though at different velocities depending on their masses. As they rush through the suppression and extraction electrodes, some electrons are scraped off. Most of these are trapped due to a negative potential on the suppression electrode. These low-energy electrons form a supportive sheath, which prevents the beam from spreading due to the mutual repulsion of the positive ions. Electrons not trapped by the extraction assembly are drawn back to the positive arc chamber and create X-ray radiation that must be monitored. The beam then encounters a large curved electromagnet called a mass analyzer. This is where single-charged phosphorus ions are separated from all the other species in the beam. As the beam enters the curved magnet, the ions move in circular arcs, depending on their masses. By adjusting the strength of the magnetic field, the charged ions with lighter masses are driven into the inner wall. Heavier ions strike the outer wall. Only a pure beam of single-charged phosphorus exits through a resolving aperture. The water cooling system dissipates the heat generated by the ions that are striking the walls of the magnet. For ions to penetrate a specific depth in the silicon wafer, they must reach a certain kinetic energy. This occurs in the acceleration column and is determined by the ion charge state and the electrical potential. Most implantations use the more stable single-charged ions. Double-charged and triple-charged ions can be used to increase the kinetic energy. However, since fewer of these species are generated in the source, this lowers the beam current. In this high-energy implanter, extremely high kinetic energy is created by an RF linear accelerator. It is made up of 12 barrel-shaped resonators packed together so their electrodes line the beam line. Only 8 can be seen from this side. On the other side, we find 4 resonators. Resonators are filled with sulfur hexafluoride gas, which can withstand high electric fields without arcing. They are fed RF voltage at 13.5 megahertz and generate ion beams up to 5 million electron volts. This insulates the resonators from the voltage, which spreads through a coil to the round electrode tips. The focusing assembly inside the beam line consists of quadrupole lenses on each side of the 12 electrodes. These lenses use magnetic fields to focus the beam. Applying alternating potentials to the electrodes accelerates the beam to its final speed. When the sine wave voltage is negative, it attracts positive ions and accelerates them toward the electrode. Changing the electrode potential to positive repels them, giving them additional energy as they move past the electrode. The beam then goes through a final energy magnet, where it is again bent to eliminate any multiple charged ions or neutral species. Once the beam is stable and all parameters are properly adjusted, The flag Faraday monitoring the beam's current moves out of the way, and implantation begins. As the rotating wafers move into the beam, phosphorus ions bombard the surface. The ions enter the silicon substrate through the exposed regions, causing extensive atomic scale damage. As dopant electrons interact with the silicon electrons, some of the initial energy is lost with electronic stopping. Most is lost, however, with nuclear stopping, as the ion collides with the silicon atom. The ricocheting effect damages the lattice by displacing about 1,000 silicon atoms before the ion reaches its final range. A Faraday cup behind the slit captures a sample of the beam with each rotation and monitors the number of implanted ions. Positive ions become neutralized in the substrate. This flow of 1 electron for each implanted ion is measured by the dose control system. When the correct number of ions has been implanted, the flag Faraday blocks the beamline and ion implantation stops. The wafers then undergo a thermal process to anneal or repair the substrate damage. At about 1,000 degrees centigrade, thermal energy reestablishes the covalent bonds. To create the deep N well, thermal energy must be maintained.